Swayam Prabha, free DTH channel for education.
In today's class, we are going to talk about some of the applications of the second order ODE, especially the constant coefficient. Okay, second order ODE with constant coefficient. We have already seen some of the example problems and then other details we have seen. So today we are going to see some simple example problem, especially from the mechanical engineering and electrical engineering problems. And the mechanical engineering problem, whatever I'm solving, that you can that is also applicable for some of the structural engineering problems also. Okay, so we'll see that. See, for example, why do we need to discuss about this? There is overdamping, underdamping, and critical damping is there. So, for example, you know this. Whenever you watch the Hollywood movie, okay, like either it is a dinosaur movie or any other movies, you can see that there is a bridge called Brooklyn Bridge. Always they will broke that bridge. Okay, in that movie. So now similar kind of thing, what we are going to do is that suppose you are building a bridge, you are a civil engineer or you are a mechanical engineer. What you want to do is that you want to construct a suspension bridge, okay, between two cities or some bridge you have to construct. Now what we need to understand is that whether the bridge which you are constructing, the suspension bridge which you are constructing, so it is going to be attached to some string or it is going to be attached to some pillars, etc. So whether it is going to be sustainable or not, okay, whether we can produce a sustainable things or not, okay, the bridge or the other things. Okay, so in that case what we need to understand is that you got to solve, you will be developing a differential equation, okay, and that differential equation you need to understand whether you are going to get a damping, over damping, or critically damping, or under damping you are going to get. Okay, so depending on that you can change your load, okay, the payload, or you can change the spring constant or the spring material or whatever you want, the corresponding materials which you want to change, you can change it. Okay, so that's what this is important. So we are going to see a simple problem first. For example, we have a you might know, like in the school days you might have done this experiment. So attach a string over here, okay, and then attach a mass here, okay, and then you just pull it over here. Then this is going to keep on oscillating. After what stage it is going to oscillate, and from that you will find the frequency, and then you will find the natural frequency omega, etc. You will find, and then you will measure the spring constant. So these are all the exercises you might have done in your physics classes in the school days mostly. Okay, the same thing we are going to do using the differential equation. What I have is I have a string, okay, where I am attaching a ball. Okay, the ball weight I will the ball, the iron ball which I am attaching. Okay, for example, I have a coil. This is the spring I have where I am attaching a coil. Okay, that coil, what I am going to do is the ball, what I am going to do is that I'm just going to stretch it down, or I'm just going to bring it down. Okay, so it means I'll just pull this over here. Then what will happen? This is going to lead to some kind of force is going to be applied over here. Therefore, this will be expand or it will be shrinking depending on the force you are applying. So once you leave that, what it is going to do, it is going to keep on oscillating. Okay, it is going to keep on oscillating. After a certain stage, it will be stopping. Okay, so those one we will find it. So in school experiment you might have studied, you will be measuring here, and then you will measure like what is the length, etc. From that you will find what is the frequency, etc. You will be finding. Now the same thing we are going to do. Okay, so we just keep, for example, I just stretch it down. Okay, and in that case I call this position as initial position. Okay, this is called as initial position. So here the ball is going to move a displacement, so I call it as y. There is a displacement from here to here, so I call it as a displacement it is going to make. Okay, so every time it is going to oscillate, so y is going to make some kind of displacement is going to come. Okay, therefore I can write y as a displacement. Let me write y, because in the y direction I'm just against the force, or helping the against the gravity, or helping the gravity to do that. So y is displacement I'm just going to put, therefore I'm going to pull, etc. I'm going to do. Then y dash is going to become like velocity. Okay, and y double dash is going to become like acceleration. Okay, these are the things I have. Now what I'm going to do, I'm going to solve a problem for this one. Okay, so the initial position I have. Now this is going to form an undamped system which we are going to get. So let us see that what is undamped system, etc. in this class. So now what I'm going to do, I'm just going to solve simple problem. So I have an object. Okay, this object weight is, the object weight is 9.8 kilogram. Okay, the object weight is 9.8 kilogram. And it is given that second thing what it is given is that the stretch of the string, okay, the string is stretched, okay, the stretch of the string is given as 20 centimeter. Okay, stretch of the string is given as 20 centimeter. Now what I got to do, find the equation of the motion. Okay, you got to find how the iron ball or the spring or the mass, how it is going to move. Okay, how the equation of the spring is going to be there. Okay, once I release the ball with the from the equilibrium position. So this is the equilibrium position. From there, if I release, what is going to be the equation of motion? Okay, we need to find that. Okay, so it is given that the another information given is that it is given that v dash equal to 14 meter per second. Okay, 14 meter per second. But it is upward, therefore I'm going to keep like v dash equal to minus 14 meter per second. Okay, minus 14 meter per second. I'm going to keep it. So now let us see. Since I have mentioned already y dash equal to velocity, so initially I am giving this one, so I'm going to call this one as y dash sub 0. Okay, y dash sub 0 is going to become like minus 14 is going to come. Now we need to obtain the model for this one. So for this, we are going to get the help of Hooke and Newton. So according to the Hooke law, what you have is you can say that F1 is equal to minus ky, okay, where y is the displacement and k is the spring constant which I am going to have. Okay, and then I have F2. F2 is nothing but due to the Newton's law, I can get that m into mass into acceleration. Acceleration is y double dash, so m into y double dash is going to come. Since F2 is equal to F1, I am going to have my double dash equal to minus ky is going to come. Okay, minus ky. So I can write as my double dash plus ky equal to 0. I can write it. Okay, this is going to be my equation of motion in this problem. Okay, because I'm ignoring the rest of the things. So of course, we will have some air resistance, etc. will come to the picture, so that we will model it later. At the moment, I'm just assuming there is no friction, there is no air resistance, etc. So in that case, my double dash plus ky equal to 0 is going to be the solution. Now what I'm going to do, so in this case, since I'm assuming the remaining things as negligible, or I'm just saying it is 0, so what I'm going to have is that my equation of motion is going to be my double dash plus ky equal to 0. Okay, so this is going to be my equation of motion is going to be there. Now what I need to find, I need to find my m and k. So it is given that w is equal to 9.8 kilogram. Okay, so w is nothing but m into g. Okay, m is it is given that 9.8. Okay, so g is already 9.8. Therefore, what you can get, okay, 9.8 into 1 is going to be 9.8. Therefore, you are going to have m is equal to 1. Okay, m is 1 means this is going to become like y double dash plus ky equal to 0 is going to come. So in fact, you can write this as y double dash plus k by m y equal to 0. You can write it. Okay, y double dash plus k by m y equal to 0. You can write it. So y double dash plus ky equal to 0 is there. Now I got to find what is my k. So for k, what I need to do, I have to use this again, the relation mg is equal to ks. I got to write because these two are same. So mg at that point I'm going to have. So this is the relation I have. Mg is equal to ks. Okay, because I'm pushing down, I'm just pulling it down. So therefore, it is going to be that the stretch of the string, etc. So s equal to 20 centimeter means it is going to become like 20 by 100. Okay, 20 by 100, it is going to become like 1 by 5. Okay, so mg is equal to ks. Mg is nothing but 9.8 already. So 9.8 equal to k into s is nothing but 1 by 5. Therefore, you are going to have k is equal to 49 is going to come. Okay, therefore, in this case, you are going to have y double dash plus 49y equal to 0 is going to come. So this is my equation of motion for the problem given in the example number 1. So on the other condition given, y dash of 0 equal to 14 minus 14 is there. Okay, this is a initial value problem I have. Y dash of 0 is given as minus 14, and initially it is red. Therefore, y of 0 I call it as 0. Okay, so these are all the initial conditions also given to me. Now I can solve this problem and I can obtain the solution for this problem. Let us solve it and then obtain the solution. So let us see that. So in this case, what I'm going to have, the time dependent problem. So y is a function of t, I can write. So in that case, I can write the auxiliary equation. So the auxiliary equation is going to become like, since y double dash plus 49 y. So for example, I can take this problem. So in this problem, it is going to become like r square plus k by m into y equal to 0 is going to come. So I call this k by m as omega square. Okay. So I call this k by m as omega. Okay. Omega is going to become like omega square. So omega, therefore this is going to become like r square plus omega square y equal to 0, where omega is nothing but square root of k by m. Okay, so these are the information I have. Now in our problem, what is my omega? Omega is going to become like 7i. So for this problem, what is the solution? The solution is going to become like, the root is going to become like r is equal to plus or minus I omega is going to come, and solution is going to become like y is equal to a cos omega t plus b sin omega t is going to come. Okay, in general. So in our case, omega is nothing but 7. Therefore, you are going to get y is equal to a cos 70 plus b sin 70 is going to come. Now already y of 0 equal to 0. Therefore, you are going to get a equal to, so a equal to 0, because y of 0 means it is 0. A plus this is already 0. So a equal to 0 is going to come. Okay. Y of 0 equal to 0 means y of 0 equal to 0 implies a equal to 0. Now y dash of 0 equal to minus 14. Okay. Y dash of 0 equal to minus 14, which implies I got to differentiate this one. Therefore, I'm going to get 7b cos 70 is going to come equal to minus 14. Okay, I got to apply y dash of 0. Therefore, this is going to become like 7b. Okay, 7b is equal to minus 14 is going to come, which implies b equal to minus 2 is going to come. Therefore, what I'm going to have, b equal to minus 2. Therefore, what I'm going to have for this problem, okay, for this problem, so this is going to become like y is equal to minus 2 sin 70 is going to come. This is going to be my solution. Let us see the graph of the problem. The graph of the problem is like this. Okay, so this is going to be the minus 2 sin 70 curve, okay, which is going to oscillate. So it is going to keep on oscillating. Okay, it is going to be a never ending, because minus 2 sin 70 is there. So it is going to keep on oscillating. Means if you are just pulling it down and leave it as it is, in that case, this is going to keep on oscillating. It will never end. Okay, keep on oscillating, it will never end. Now, this is not the real case. Okay, in the reality, it will not come. So we'll see that some more things like damping and friction, air resistance, etc. will be adding. So in that case, you'll be getting some different kind of problem will come. So there will be extra term will come, and then we'll solve that problem also. So next, what we are going, I'm just going to give a similar kind of problem, like I have y double dash plus k m y equal to 0. Now what we are going to do is that we are going to solve a similar kind of problem. I'm just not going to solve, I'm just going to give the idea how you are going to get. Okay, similar kind of thing, y double dash plus omega square y equal to 0. So this is going to be the solution for this kind of problem. Okay, this is going to be the equation of motion, a similar kind of problem. Now suppose a similar kind of problem, because you have oscillated the string, right? Now instead of that, suppose whenever you are taking a bath in the morning, if you are not taking the shower bath, okay, or you are taking in a bucket or in a tub of water, in that case, in the childhood or sometimes nowadays also, you may be playing something like keeping the watermark inside the water tub and then just press it down, then it will be keep on oscillating. Okay, so this is the one which we are going to solve it now. So what I have is, I have a bucket of water. Okay, I have a bucket of water, let us say. Okay, I have a bucket of water. So what I'm going to have is that I'm going to have a cylindrical bag. Okay, or I just say like a mug is there, where what we are going to do is that this is the 60 centimeter buy is that I'm just going to push it down. Okay, so this is floating inside the water. So I have a water here. This is water is filled here. What I'm going to do is that I'm just pushing it down. So if it is pushed down, what it is going to do, it is going to displace the water. Okay, and what you are going to have is that it is going to be oscillated. Okay, so if you just keep it down, press it down and then release the hand, then it will be keep on oscillating this one. Okay, if it is awfully filled, etc. So now what we are going to do is that we are going to find the weight of this buy, how much weight it is going to be there. Okay, depending on the conditions given. So it is the water, which is it is displacing the water in the vertical direction. Okay, so it is floating in the this bucket, or you take it as a tub, release it. The oscillation, okay, it is going to vibrate. The vibration period is going to be 2 seconds. Means once it reaches over here, okay, To reach that place again, it takes 2 seconds. Okay, it vibrates with the period 2 seconds. Mostly mechanical engineer people know how to calculate this one. So y double dash plus omega square y equal to 0 is going to be again governing this kind of problem. So in this case, the question asked is what is its weight? What is the weight is going to be there? Once again, you need to solve this kind of problem, and then you got to find the weight of the by. Okay, again, the motion of this one you can discover using this kind of equation. Now another problem, you have a U-shaped tube. Okay, you have a U-shaped tube. For this U-shaped tube, what you have is that again a similar kind of problem. So it is filled with some water. So the diameter of the U-shaped tube is like 5 centimeter is there. Sorry, 4 centimeter is the diameter of the U-tube is the U-shaped tube is 4 centimeter. Okay, again you can model the similar kind of thing with some oscillations, etc. Same kind of logic is going to come. Y double dash plus omega square y equal to 0. Again, I give some more problems like m equal to 1 and k equal to 0. You can solve this. So substitute m and k here. Okay, and then you can calculate this kind of problem solution, and then you can discuss much more cases. So in general, suppose you have a y double dash plus omega square y equal to 0 is going to be there. Okay, so in general, in this case, what you are going to get is that you are going to get the undamped system. So you are going to get a, for example, here you have seen that there is a sine curve was there. Okay, now what you are going to do is that you are going to get now what you are going to do is that you are going to get something like y equal to a cos omega t plus b sin omega t. This one I can write it as y equal to a cos omega t minus theta. I can write it. Okay, omega t minus theta I can write it. So here a is so instead of a, I'll put it b here because already there is a a. So in general, you will write this way. Okay, a cos omega t plus pi used to write in the mechanical engineering and the physics people used to write. So that a they call it as amplitude. So here I have already used a, therefore I'm going to call it as c. The c is nothing but the amplitude. So the amplitude is here and the phase difference is here. So the same way you used to write it in the mechanical engineering or some of the electrical engineering problem. For c and a, you can c and theta, you can find it from here. Expand this one, use cos a plus b formula. You can just expand that one. So you are going to get c cos omega t cos theta plus c sine omega t sine theta is going to come. Equate those things, and then you can find your c and theta. That c and theta is going to become like c is going to become like square root of a square plus b square, and theta is going to become like tan inverse of p by e. So from that, you can calculate your the oscillation. Okay, how much time it is going to take the oscillation means the t you can calculate the time period between the oscillation you can calculate. So that is going to be omega by 2 pi, or the natural frequency you can calculate, which is nothing but 1 by t. That is going to be omega by 2 pi. Okay, so this is going to be given the undamped system, how it is going to oscillate, etc. is going to come. So we'll discuss about the undamped system once we introduce the friction force, etc. So now what I have a second thing. Motorbike suspension means I'm going to introduce some more term for this problem. What I'm going to have is that I'm going to introduce friction also, because now I didn't include any friction. In the next problem, I'm going to include the friction and then I'm going to solve that. In that case, you are going to get the complete second order ODE, which we have discussed earlier. Okay, so what I have a like the motorbike. So the motorbike will be having some kind of dashpot. So in that case, you are going to have a friction, etc. is going to come, because that is going to reduce the oscillations much further. So for that purpose, we require the dashpot, etc. So let us see that motorbike suspension and the rover suspension, etc. For example, if you see the spacecraft or the lander which is going to land in the moon or Mars, in that case, suppose because it is going to come from a long distance and it is going to jump over there, if it is jumping there, what is going to happen? It is going to be bounced back. Okay, it is going to bounce back because it is coming very, very large speed. If I just leave no spring or etc., what it is going to come? It is going to be just hit on the ground and it is going to be blast. Okay, it is going to be wasted. Okay, whatever I invest. Instead, what they will introduce is that they will be introducing some constant so that it will be jumping. Okay, the jump will be just making some small jump it will make, and then they will be having some other setup so that it will be controllable. You can do that controllably, and then you can keep it in the ground. Okay, for that purpose, either it is a lander or you have a aeroplane or you have a spacecraft, whatever you have, there will be a lander suspension will be there. So that suspension is going to carry out whatever the force which was exerted due to that impact. Okay, so that will be taking care, and then it will reduce the burden to us. That's what the motorbike suspension is going to do, because otherwise you will get a back pain, or you will be just move out of your car or vehicle, whatever you are traveling. Okay, so for that purpose we have the spring. Now what we are going to do is that the motorbike suspension, in the reality, so in this problem we were oscillating, but we neglected the friction, or we assume that there is no friction, but in reality always there will be a friction. The friction is going to give the oscillation die slowly. Due to the friction, the oscillations will die slowly, which is called the damping. And you will have a air resistance, which is called physical damper or the air dashpot. Okay, the dashpot also will have. So air resistance will be the physical damper you can produce, and then you can produce some dashpot. These are all things it is going to make our oscillations die slowly. So what is damping? Damping is a friction force which is proportional to the velocity of the mass. Okay, proportional to the velocity of the mass, and acts in the opposite direction, which is going to act in the opposite direction. So in that case, you are going to have y dash. I already mentioned y dash is the velocity. Okay, so in that case, your equation is going to become like y double dash plus cy dash plus ky is going to come. Okay, so y double dash plus ky, my double dash plus ky already we know is equal to 0. We have already proved for the previous case. In that case, there was no friction assumed. Now I assume friction, therefore that is going to become like these two together is going to balance this friction which I am going to introduce, is going to balance these two oscillation, the undamped oscillation, whatever I have. So that is going to make some balance. So in that case, I'm going to have a friction. So we are going to get cy dash is going to be there. Okay, so minus cy dash is going to be there. So I can bring it on the left hand side. So we are going to get that. So in this case, I can write that equation as again y double dash plus c by m y dash plus k by m y equal to 0 is going to come. Okay, so in this case, again I can calculate what is my auxiliary equation, r square plus c by m into r plus k by m equal to 0 is going to come. So I can find the root of this equation. This is going to become like minus c by m plus or minus square root of c square by m square minus 4 k by m divided by 2. Okay, so this I can write as minus c plus or minus square root of c square minus 4 and k. So m square I'm taking it out. Okay, this is going to become like m is there. So this is going to become like 2m. So I can write it as minus alpha plus beta plus or minus beta. Okay, where alpha is going to become like c by 2m and beta is going to become like c square minus 4mk square root of c square minus 4mk by 2m. Okay, so this is the one which I have. Now I have this term. Okay, c square minus 4mk. This is the term I'm going to discuss, which is called the discriminant. So depending on the discriminant, our root is going to change. So that's what we are going to discuss now. Okay, so you have a case like r. So you will get two roots here. One is going to be minus alpha minus beta. Another is going to be minus alpha. One is going to be minus alpha plus beta. Another is going to be minus alpha minus beta. Okay, so in that case, I'm going to calculate depending on the c square minus 4mk. I'm going to say whether if it is greater than 0, less than 0, and equal to 0. Okay, I'm going to discuss the case. So c square minus 4mk is greater than 0 means I'm going to get c square is greater than 4mk. So in this case, I call it as overdamping. Okay, this is called overdamping. Okay, so less than 0. So in this case, I'm going to get k is here. C square less than 4mk is going to come. Okay, so in this case, it is called underdamp. Okay, underdamp. And this case, I'm going to get c square equal to 4mk, and this is called critically damped. Okay, critically damped. So let us see why the naming is there. So by pictorial representation. So overdamping. What is meaning of overdamping here? See, if it is c square is greater than 4mk, your roots are going to be real and distinct. Okay, it is going to be real and distinct. Therefore, I can write the equation as follows. So I can write it as y equal to c1 e power minus alpha minus beta t. Okay, and then plus c2 into e power minus alpha plus beta t. I can write it. Okay. So I can see that this is an exponential one. So as t tends to 0, suppose your alpha minus beta and alpha plus beta is both are greater than 0. Alpha is greater than 0 and beta is greater than 0. And b square means I'm having alpha square minus beta square. Alpha square minus beta square is greater than 0 in this case. Okay. If alpha square minus beta square is greater than 0, in that case, you are going to get alpha minus beta and alpha plus beta is greater than 0. Okay. So in this case, what you are going to get, both of them, either it should be negative or it should be positive. Okay, either it should be completely negative or it should be completely positive. Okay, so if one of them is positive and one of them is negative, we are not going to get that. So in this case, what it is going to come, if both of them are suppose positive, then what it is going to come, it is going to become like this is as t tends to 0, this is going to become 0 and this is going to become 0. Therefore, y is going to become 0. If alpha minus beta and alpha, now similar, so that is called overdamping. Now underdamping or so critically damping, we'll see. So in critical damping, what you are having c square equal to 4mk is there. So in that case, our root is going to become like my solution is going to become like c1 plus c2t into e power minus alpha t is going to come. Okay, because beta is already become 0, so I am going to have minus alpha t is going to come. So in that case, what you are going to have, this is similar to overdamping only because you have an exponential term. So if you are going to get like a 0 is going to be reached soon. So if the damping is reduced little, it will oscillate. Okay, if you reduce the damping, if damping is reduced little, it will oscillate in this case. Okay, because you may get a reach the c square less than 4mk case may come. Okay, so physical systems. So in reality, the physical systems are either over or under damped will be that. Critical damped will be mostly will not happen. So for underdamping, what I have, c square is less than 4mk. So this is the case we are going to discuss. So c square is less than 4mk means your beta is going to become like, this is going to become like imaginary quantity. So therefore what I'm going to do is that I'm going to write this as I into b square, I into square root of 4mk minus b square minus c square I'm going to write. Okay, I into 4mk minus c square I'm going to write divided by 2m is there. Okay, divided by 2m. So I just call this one as omega. This quantity I call it as omega. So I'm going to write omega is equal to square root of 4mk minus c square by 2m. Okay, or I write it as, okay, so this I write it as, I just bring that inside. So this is going to become like square root of, I just bring it over here. Therefore, this is going to become like 4m square is going to come. Therefore, I can write it as k by m. Okay, k by alpha t. Okay, this I am going to call it as omega. Using omega, I am going to write a cos omega t plus b sin omega t. I can write where omega is this one. So in this case, what you are going to get, or I can write as in the previous case we have written c cos omega t minus theta. Same I can write as c into e power minus alpha t. Okay, cos of omega t minus theta I can write it same way. Okay, so e power minus alpha t is going to be there. So in this case, what you are going to get is that a similar kind of graph you are going to get, but since there is a c e power minus alpha t, so suppose your alpha is going to be a decaying one, then means my alpha is positive. So that means what you are going to get is you are going to get a decaying curve. So in that case, you are going to get your curve is going to be bound between these two curves, c e power minus alpha t and minus e power minus alpha t. So in between them, that is going to be there. So that's the reason it's called underdamping system, because you are going to have a oscillations over here that is going to be decaying after certain stage. So that is the reason it is called underdamping system. Okay. Now next case, next problem. So for this we'll see some problem. So there is a Honda bike. Okay, you might have traveled in that. So Honda bike is there. That the weight of the bike is 109 kilogram and weight of the rider is 67.4 kilogram. Now what we are going to do is that when the rider mounts the bike, okay, when the rider mounts the bike, it will be immediately giving some compression. Okay, the suspension compresses the dash part or whatever you call the spring, that is going to be compressed like 9.8 centimeter. Then it comes to the rest at equilibrium. Now what we have is the suspension system provides a damping. Okay, the damping also provide, which they have given 360 times the vertical velocity. Okay, 360 times the vertical velocity of the bike and the rider. Okay, together. Now what we need to do is that we have to calculate we have to model this and then we have to solve the problem. So what I have is I have W is equal to mg. Okay, W is equal to mg, which is nothing but the mass. Here the mass weight we have to consider together the bike plus the rider weight. Okay, so in that case I'm just taking 176.4 kilogram and it stretch they have given 9.8. Okay, so 9.8 centimeter, which is nothing but 0.098. Okay, so that's what we have. Now what we need to do is that we need to solve this problem. We need to identify whether it is underdamping or overdamping and what is the solution is going to be there, etc., etc. we have to find, and I will introduce some more conditions and then we'll solve the problem for this case. Okay, so what we have, for this problem, the information is given is that you have Ws equal to mg. Okay, Ws equal to mg, where mg is nothing but 109 plus 67.4, which is going to be 176.4 kilogram. Okay. Then what you have stretch S is nothing but 0.098. Okay, 0.098 is there. Then again you use the mg equal to ks formula. Okay, mg equal to ks, and then find your k. What is your k? You find it. Okay, mg equal to ks and k equal to 1800 is going to come, and it is given that cy dash is going to be like it is already given that 360 times the velocity. Means they have given the damping force is nothing but 360 times the velocity. That means cy dash is going to become like 360 into y dash is going to come. Therefore, you are going to get my double dash plus cy dash plus ky is going to become like you are going to cut. You already found k. So this is going to become like 1800 y, and cy dash is nothing but 360 y dash. Okay, and then m is nothing but you have already 176.4 kilogram. Okay, mw, g you substitute 9.8, and then you can calculate your w is going to m you can calculate, m is going to become like 18, so 18 y double dash is going to come. Okay, so in this case also they have given when the bike was in the air contacting the ground, the wheel was hanging freely and the spring was uncompressed. Okay, when the bike is in the air, therefore the wheel is 0.098 meter below the equilibrium position. Below the equilibrium position, it is 0.098 meter. Therefore, what you have this information. C already we know 360. Okay, K now we have to see like whether it is going to be overdamping or underdamping. So C square is going to become like 360 square, and 4mk is going to become like again. So this is going to become like 360 square. Okay, C square is going to become like 360 square, and 4mk which is going to be 1800 into 18 into 4 into, yeah, that's all. Okay, 4 into m into k. So this is going to become like I can write it as 4 into 18. So there is a 2 zeros here. Okay, 2 zeros are there. So 4 I can write it as 2, and this one 9 into 9 is that. Therefore 4 into 9 square. Therefore it is going to become like 360 is going to come. Okay, so 3 this is going to become like, so I can write it as 360 square here also. Okay, because 1880 into 4, so that is going to become like 360 square once again. So therefore this is going to become like critically damping. It is not underdamping, it is going to be critically damping. Therefore my y is going to become like C1 plus C2 into C2t into e power. I got to find what is my alpha. Alpha is going to become like 360 by 18. So that is going to become like 20. Therefore you are going to get by 2. So that is going to become like 10. Okay, this is going to become like minus 10 t. Okay, so minus 10 t is going to come. So in that case, you can obtain this as your y. Okay, y is going to be this one. Now y of 0, it is given that y of 0. What is y of 0? We got to see y of 0 is nothing but 0.098, because it was mentioned that s is 0.098, so that is going to be that. So it is going to be 0.098. So in that case, you are going to get C1 is going to become like, so this is going to be 0, this is going to be 1. So C1 is going to become like 0.098. Okay, C1 is going to become like 0.098. Now see y dash, you got to find y dash of 0. Y dash of 0 they have given us. So I give another information. Suppose y dash of 0 equal to 10. Okay, suppose y dash of 0 equal to 10, then what is your y is going to be there? That also we can find. So y dash of 0 equal to 10 means you can substitute over here. So y dash is going to become like C1 plus C2t. Okay, minus 10 into e power minus 10t is going to come, plus again I got to differentiate this one. This is going to become like C2 e power minus 10t is going to come. Okay, substitute over here. So C1 I know already, C2 I know. So y dash of 0 substitute here, then you can calculate this one. So that is going to become like you are going to get your C2. So from this one you can get your C2. C2 is going to become like 10.98. Okay, substitute it and then you can simplify. That is going to become like 10.98. Therefore your y of t you can substitute and then you can calculate the answer for that. So this is the graph for the problem. So you can see that at it is just exponentially growing. Okay, almost it reaches 0.48. Okay, the damping, it is the problem is reaching almost 0.48, and then it is coming to the decay mode after certain stage because of e power minus 10t. Okay, so this is happening in the motorbike suspension problem. Now next one, we will see the RLC circuit. This is for the electrical engineers. Okay, so in the RLC circuit, what you have is that you have a resistor and inductor. Okay, so and then capacitor. So these are all the things available. So here what you have is that you have a resistor RLC circuit is there. So for this RLC circuit, what we are going to find is that again we are going to develop a similar kind of second order ODE problem. So a current in the circuit causes a voltage drop Ri across the resistor. Okay, there is a resistor and voltage drop Li does across the conductor. Okay, so in general you may have like capacitor, conductor, inductor, resistor, etc. will be there. So in this problem we are going to have this Li does across the conductor. What we have is Kirchhoff's law. Okay, using the Kirchhoff's law we are going to obtain the second order ODE problem. So some of these two voltage drops. Okay, you have a voltage drop. One is due to the drop Ri across the resistor, okay, which is due to the Ohm's law, and then Li does, which is due to the which is across the conductor. You are going to get that. So using the Kirchhoff's law, you can find that what is the electromotive force. Okay, drop equals. So in that case, you can calculate this one. For example, in this problem, what you are going to get is that you are going to get I dash plus R by L into I equal to E by L is going to come. Okay, this is going to be there. Now what I'm going to do, either I can differentiate, I can use some other method to calculate the values. For example, here you have the RLC circuit. So in the RLC circuit, the circuit is obtained by adding a capacitor. So I'm going to add a capacitor also over here. So in this case, it is simply the RL circuit. Okay, this is simply RL circuit because resistor and conductor both are there. Now I'm going to add a capacitor also. Therefore, in this case, you are going to get another component over there. So in the RLC circuit, you are going to have a capacitor added. So the voltage drop across the capacitor is going to be called as Q by C. Okay, so in that case, you got three things. The voltage drop at the resistor is going to be R by L. Voltage drop across the conductor is going to be Li does. Okay, so this is going to be Li does. So you can see that, and this is going to be Ri is going to be there. So that is going to be equal to the electromotive force. Using the Kirchhoff's law, I can get that, and then you are going to get that Q by C. So this one I can write. So I am just going to have this relation. So this is the relation from the electrical engineering problem. So Li does plus Ri equal to E is there. Okay. Now I have plus I have this extra term which is due to the capacitor also. For the capacitor also I have taught that is going to become like one more term which is going to be Q by C equal to E is going to be there. Okay. Now what I'm going to do, I'm just going to use this I equal to Q dash is there. Okay, I equal to Q dash I have. Therefore, what I'm going to do, I'm just going to differentiate this one with respect to T. So this is going to become like Li double dash plus Ri dash. Okay, Ri dash plus Q dash. Q dash is nothing but I by C equal to E dash. Okay, this is also I'm going to differentiate E dash of T. So either you can get this one, this R, Q, C are all constant. Okay, either you can have this one, or you can do the other way. You substitute I equal to Q dash. Therefore, this is going to become like LQ double dash because I equal to Q dash means I dash is going to become like Q double dash. Okay, LQ double dash plus R Q dash. Okay, plus Q by C equal to E. In both cases, okay, either you take this problem or you take this problem. In both cases, you are going to have solve. Either here you are going to solve for current, or here you are going to solve for the voltage. Okay, Q or I. So in both the cases, you are going to get a second order ODE problem. Once again, you can solve a similar kind of logic, and then you can get the answer for this one. So, for example, you have this problem A of D is equal to E naught cos omega t is there. Then you can calculate your annihilator, and then you can solve this problem, which we have already solved one or two problems. Same way you can solve this problem also. So for which you are going to get this one. And then we have some more discussions over here. For example, if you have the reactance, okay, that I can write as S equal to omega L minus omega C. And impedance you can write as square root of R square plus S square. So these are the calculations once again obtained from our problem what we solved in the RLC circuit or the second order ODE problem. So I'm just highlighting those things. Similarly, this one like the way we have written in the undamping and overdamping problem, what we have written is you have written y equal to c cos omega t minus theta. Same way here I'm writing it as I naught sin omega t minus theta, where I naught is going to be the same kind of formula, square root of a square plus b square, and tan theta is going to become like minus a by b, or s by r is going to come. Okay, so using the relations which we got. So the general solution, you can write it in this way. Okay, again here we will there will be a discussion which you can refer your some of the electrical engineering book. Again here r square minus 4l by c is there, where again you will get some kind of discussion like underdamping, overdamping, etc. Similar kind of discussions will be there for the RLC circuit also. So the in actual circuit r is never 0. Okay, there will be always some r will be there, so it is never 0. Therefore, what you are going to have when IH tends to 0 in this equation, what you are going to get is that you are going to get t tends to infinity, you are going to get IH tends to 0. Practically it reaches 0 relatively short time. Okay, practically it will be reaching quickly the 0 value. Okay, and if you have a transient current, you can again calculate that using this formula IH plus Iphi, which tends to the steady state current IP. Okay, after a few seconds, the output will be a harmonic oscillation. That's the reason you have seen that all the the current circuit will be having some kind of oscillation will be there. Now, last problem in many of the competitive exams and other problems. So the problem is I have suppose y double dash plus x square y double dash plus p of x into y dash plus q of x into y equal to 0 is given. Okay, it's 0, and its Ranskin is given as okay, w of x equal to 6x cube is given. Okay, the question is, can we find p of x? Okay, let us put this as capital P of x. Okay, can we find this one? Okay, so that is the question which is appearing in some of the competitive exams like CSA or GATE exams question. So let us see this problem. Suppose this one we can solve it easily. Suppose y double dash plus p of x into y dash plus q of x into y equal to 0 is there. Then in one of our classes we have derived that w dash equal to minus pw will come. Okay, from that only we derived the Abel's formula, and then we used to find that. So in this case, you can see that p is equal to minus w dash by w is going to be there. Okay, minus w dash by w is going to be there. So in this case, we are going to solve this problem. So it is given that minus w dash is going to be w. So in this, we got to convert this problem in this format first of all. Okay, after solving this one. So here it is going to become like 18x square divided by 6x cube. Therefore, this is going to become like 3 by x minus 3 by x. Okay, minus 3 by x is there for p. Now what we have to convert this problem in this format. Therefore, what you are going to have y double dash plus p of x, capital P of x, okay, by x square into y dash plus q of x by x square into y equal to 0. In that case, this is exactly the similar form. Therefore, your P of x is going to be, your small P of x is nothing but P of x by x square. Okay, what is your P of x? P of x is minus 3 by x. So minus 3 by x in equal to P of x by x square. Okay, therefore your P of x is going to be minus 3 by x into x square. Okay, so this is going to become like minus 3x. Okay, so this is the problem. Usually some of these problems will be asked in the civil some of the CSIR or GATE exam question. Okay, so some of the exercises I will provide which you can do. So this is one of the practical problem which I am just highlighting, which I was solving in the solving, or we were asked to solve this problem from NASA and ESA. Okay, so the question is, you have a lander system. Okay, NASA is planning to mission. Was planning for a mission to Mars. Already they sent. Okay, so they were planning a mission to Mars. Okay, in order to save the money, what the engineers and the NASA have decided is that they try to adopt one of the moon landing vehicle for the new mission. Okay, for the Mars mission, they want to adopt the moon landing vehicle. The problem is that the gravitational force in the moon will be different. The gravitational force in the Mars will be different. Both are completely different. So what are we going to do if we are going to use the same vehicle in that system? Okay, because the suspension system, everything will be designed for that. The question is, can we use the same kind of vehicle in this Mars landing? Okay, the moon landing vehicle, can we use it for the Mars landing? That's the question they were trying to answer, because the gravitational force both are different. Okay, so in that case, you need to find that. So the acceleration results from the gravity of the moon, which is given as 1.6 meter per second square. whereas in the Mars it is 3.7 meter per second square. Okay, so now what we have the lander. The lander has a mass of 15,000 kilogram. Okay, 15,000 kilogram, and the spring is 2 meters long. The spring, whatever I have shown here, is 2 meters long. Okay, when uncompressed. The lander was designed in such a way that the lander is designed to compress the spring 0.5 meter to reach the equilibrium position under the lunar gravity. Due to the lunar gravity, it is going to. And the dashport which imparts the damping force is equal to 48,000. Okay, 48,000 times the instantaneous velocity. Okay, of the lander. So almost whatever we solved in the similar kind of thing, you can design this also. Instantaneous velocity of the lander. So what we need to do is that you need to set up the differential equation that models the motion of the lander when the craft lands under motion. Okay, the same thing what we designed in the previous one, the same kind of thing. So when time t equal to 0 denote the instant the lander touches the Mars surface or the Moon surface, the rate of descent of the lander, which is controlled by the crew, or they wish to control from the lab, okay, the NASA lab, so that it is descending at a rate of 2 meters per second. It is slowly descending, okay, 2 meters per second when it touches the top. Now, what is the equation of the motion of the lander of the motion? Lander on the Moon, that you need to find. First, for the Moon, you need to find. Now, next one, if the lander is traveling too fast, okay, when it touches it down, when too fast, what it will happen, it could fully compress the spring and bottom out. Means it can just go, it will just break out, or it will just go jump out in this case. So if it is bottoming out, what will happen? It could damage the landing craft. It can just make some kind of, it can just oscillate, and then it will just keep on jumping, and it will make some multiple jumps, etc. It can do. Okay, so this could damage the landing craft. And it must be avoided at all costs. So that should be avoided at any cost, okay, because that should not happen. So grab the equation of the motion, which you found it in the previous one. If the spring is 0.5 centimeter, okay, suppose the spring is 0.5 centimeter long when fully compressed, will the lander be tangent of bottom out? Okay, that question you can answer. So suppose assuming engineers make no adjustment to the spring of the tamper, which they got it from the Moon lander, how far does the lander compress the spring to reach the equilibrium position in the Martian gravity? So I'm just taking the vehicle from the Moon, and I'm just trying to put it in the Martian gravity, and then I'm trying to understand whether it will be there. Next question, suppose if the lander crew uses the same procedures on Mars as on the Moon and keeps the rate of descent as 2 meters per second as we do it in the Moon, if they do, will the lander bottom out, or will it land on Mars? Okay, that also you can answer. What adjustment, if any, should the NASA engineers make to use the lander safety on Mars? The vehicle which they take it from the mission of the Moon, which they are going to use it in the Mars, can we do that? Okay, so that's the question we need to answer. So this I leave it as an exercise. You explore that, and then you can see that. Thank you.